Throughout history, man has sought control over the world around him. He learned to make clothing from the animals that he killed for food. Natural caves provided shelter that kept him cool in the summer and warm in the winter. Soon, fires were used to increase the comfort in these simple dwellings. The trees of the forest that fueled these fires were eventually put to another use. They were felled to make new sorts of homes. These structures were designed by man to further remove him from the hostility of his environment. As time passed, other changes occurred. Man not only built houses, but commercial and industrial establishments as well. As larger structures were created for manufacturing, it became apparent that controlling the environment was more than a matter of heating and cooling. The processes involved in manufacturing often added dust, smoke, or other unwanted particles to the air, so air cleanliness became a problem. The large buildings trapped air and heat, so air movement was a concern. Thermal radiation became troublesome as more heat sources were added to the manufacturing workspace. All of these environmental qualities can be directly sensed, that is, seen or felt, or perhaps smelled. But another factor which contributes to our general sense of comfort is humidity, and that is harder to detect. We generally perceive changes in humidity levels as changes in temperature. Although the two are interrelated, there is a big difference. Too much or too little humidity at a given temperature can cause losses in comfort, productivity, product life, and profit. We're inside the Impression 5 Science Museum in Lansing, Michigan. This museum's goal is to present science, art, and technology in a hands-on fashion so that adults and children will be intrigued and encouraged to explore the world of science. An extension of that philosophy is the Traveling Science Show. Presentations from the various disciplines exhibited at the museum, such as energy, sight, chemistry, electronics, and mathematics, tour schools and organizations throughout Michigan. Today, the museum's travel show director, Harmon Everett, alias Dr. Zapp, is giving a presentation at the museum on humidity.
Welcome to this demonstration about humidity. We'll start today by making a cloud in a bottle. First, you need some moisture in there, and then you need something for the moisture to condense around. I'll add some smoke particles. Not very many, but some. And then I'll pressurize the air in there and then let it expand very rapidly. And that will, as the pressure drops, the temperature will drop in there past the dew point, and we'll make a cloud in a bottle. Just like that. Now, the amount of moisture that a volume of air can contain before it starts condensing out depends primarily on the temperature. If you have 100% humidity, or saturated water vapor, at a particular temperature, and then raise the temperature, the relative humidity will drop because warmer air can contain a lot more humidity or a lot more water vapor than cooler air. If you drop the temperature, the relative humidity will rise because it will be getting closer to the amount of moisture that that temperature of air can contain. If the temperature continues to drop, the relative humidity will rise past 100%, and some of the moisture will condense out or precipitate out of the solution. Now, if it was outside, it'd condense on leaves and grass and things as dew. That's why the temperature that that happens at is called the dew point. In our bottle, it condensed out on the smoke particles as a cloud. Now, we can measure the relative humidity by using the rate of evaporation. Now, if you blow on the back, or if you lick the back of your hand like that, and then blow on it, the back of your hand will feel cool. That's because in order to become water vapor, water has to have a lot more heat energy. And it gets that heat energy from the back of your hand. It cools the back of your hand. Now, the heat energy that it takes doesn't raise the temperature of the air any. It just is used to make the water into water vapor. So moist air contains a lot more heat energy than dry air at the same temperature. Now, it evaporates from your hand. It adds heat energy, which has got a fancy name. It's called enthalpy. It adds heat energy to air at the same temperature, but it does cool your hand. And we can use that cooling effect, the evaporative cooling effect, in order to measure the amount of humidity, relative humidity in the air. If the humidity is at 100%, then not very much evaporation is going to take place. Not very much water is going to turn into water vapor, and there's not going to be very much cooling going on. If the air is very dry, then there's going to be a lot of cooling happening, a lot of evaporation. Scientists have developed a little gizmo called a sling psychrometer that uses that. It has two thermometers. One of them has a dry bulb. One of them has a little cloth wick on it that you get wet, just like that. And then you sling it around your hand, which is where the sling part of the name came from. And then you measure, you look at the dry bulb to find the dry bulb temperature, which indicates the actual temperature of the room. And then you look at the temperature of the wet bulb thermometer, and in a room that's less than 100% humid, that will be cooler because there will be water evaporating from the wick and cooling the wet bulb. There's been charts developed that show what any particular difference means in terms of relative humidity for any particular dry bulb temperature. Now, if you're sitting in a room, water's evaporating from you very much the same way as it's evaporating from this wick. And you're feeling cooler, if the room is less than 100% humid, you're feeling cooler than the dry bulb temperature would indicate. This is the room's sensible heat. If the room is very dry, you're feeling a lot cooler. Now, if you feel too cool, there's two things that you can do about it. You can go to the thermostat and turn the thermostat up. This warms the room by adding more heat from the furnace. It's using more energy from the furnace. But this is raising the temperature in the room without raising the relative humidity. So as you raise the temperature, the relative humidity will drop, and more evaporation will be taking place from you, and you'll feel cooler and get involved in that cycle. You could also add humidity. And if you add humidity to the air, one thing that happens is that the relative humidity will rise, and that will slow down the amount of evaporation from you. It'll slow down the amount of cooling effect you'll have, and you'll feel warmer just because of that. But also, humid, moist air contains more heat energy, more enthalpy, than dry air at the same temperature. You may have felt this in a sauna. If you're sitting there in the sauna feeling very comfortable, somebody comes in and pours a lot of water on the rocks, suddenly the air feels a lot warmer, a lot hotter actually. That's because there's a lot more heat energy in the same amount of air with moist air at the same temperature than in dry air. Now, if you're sitting in a room and the air is absorbing moisture from you, as it's evaporating from you, the air is absorbing it. It's also absorbing moisture from other materials in the room. Wood and paper and cloth all readily absorb and give up moisture. They're called hygroscopic materials. And dry air will take moisture from these materials, wood, furniture, paper and books and cloth, and they will shrink, the materials will shrink, and also become more fragile. Another thing that dry air does is that it's a very good insulator. In fact, it's one of the best insulators known to man. If you have fiberglass in your walls, what you're trying to do with the fibers is capture dry air and keep it in one place so that the heat doesn't transfer between the inside and the outside. If you keep the air in one place, you don't have convection currents, and if it's dry air, the heat doesn't transfer through the insulation. Now, inside a room, you want effective heat transfer. You don't want the heat sort of pooling up around the heat register. You want it to spread through the room effectively. Dry air is also a very good electrical insulator. I have a demonstrator over here, a little piece of equipment called a Van de Graaff generator. And on a dry day, it can collect up to make a spark about 13 inches long, which is collecting a charge of about 500,000 volts. People collect electrical charges too. As we walk along, we scrape up electrons from the floor or the carpet, and on a dry day, we can walk across the carpet on the way to our computer and collect a charge of about 20,000 volts, which would make a spark about half an inch long. The problem with that is that computers and other electronic gizmos that use IC chips or transistors, the components in electronic equipment work on about 5 volts, and it only takes about 100 or 200 volts to blow them up or short circuit them. Dry air insulates against that static electricity and allows the charges to build up. But as moist air allows the charges to dissipate through the moisture. I can make a fairly big spark in the dry air, but if I humidify the air around my Van de Graaff, I can't get a very good spark at all. Now, that just about wraps up our demonstration. We've talked about a lot of things that involve humidity. We've talked about dew point and 100% humidity and how they measure relative humidity. We've talked about how temperature affects what the relative humidity is, depending on the amount of water vapor in the air. We've talked about and seen how evaporation cools and affects the humidity and how comfortable a person feels in a room or its sensible temperature. We've talked about enthalpy, or the amount of heat energy that is contained, and how moist air contains a lot more heat energy, or enthalpy, than dry air does. And finally, we've talked about the insulating value of air and how dry air insulates against heat and static electricity and allows static charges to build up, whereas moist air helps the heat transfer and also allows static electrical charges to dissipate. Thank you very much for coming to our demonstration.
Well, that's what humidity is. And in the ESD experiment, you've seen just one example of how it can affect you and the world around you. The fact is, proper humidity levels are important to so many fields and professions that we can't even begin to name them all. What we're going to do is talk to a few experts in a number of fields where maintaining proper humidity is necessary to maintaining our present quality of life. We'll hear about human factors, how humidity affects you and those around you. Have you ever considered the importance of humidity in the healthcare professions or the banking industry? Well, it's very important. Proper humidity is also essential wherever fibrous materials such as wood or paper are stored, produced, or used. Finally, we'll see how proper humidity levels are important to the preservation of the documents and articles that provide the connection between modern man, our past, and the world that we've tried to control for so long. The first thing we're going to consider is how humidity affects each of us in our daily life. We're all familiar with the itchy skin that can leave us so irritable during the winter when we spend so much time in dry, heated air. Unfortunately, dry skin is only a minor problem compared to others that result from improper humidity levels.
There's an area of psychology, industrial organizational psychology, called human factors. And basically it involves a study of environmental events that affect human work performance. And these things typically include heat, humidity, lighting, cleanliness, and so on in the work environment. And it's been shown basically that extremes on any of these factors will detrimentally affect work performance. And so it's advantageous to manage all of these factors so that you get optimal work output.
What isn't often considered is the effect of humidification on human health and comfort. Humidity can have a very beneficial effect on the comfort of building occupants if it's maintained within a 40 to 60% range. It can also reduce absenteeism due to respiratory infections dramatically if it is maintained in that range. We know that the growth of viruses can be reduced substantially, specifically the viruses that are suspected of causing the common cold.
In this hospital, there's an obvious interest in maintaining patient comfort. There are many other reasons, however, for the maintenance of proper levels of relative humidity in patient rooms, ICUs, and operating rooms.
By doing this, we help control the static electricity problems as due to the gases that we use within these areas. We also help provide a better environment for the surgical staff, as well as increasing the drying time of the surgical wounds. This helps in the healing process. We also have studies that show and indicate that airborne bacteria is dramatically decreased by 50% humidity within these areas.
Computers now play a major role in all our lives. There's hardly any facet of life that isn't computerized from the moment of our birth until the day we die. Proper humidification is an ongoing concern here, too.
Correct levels of humidity are very important here at Great Lakes for the efficient operation of our computers. In fact, they're essential. Electrostatic discharges can be very dangerous to just about every piece of equipment that we have on the floor. In the past, we've had some situations where levels have dropped too low and we've lost some equipment because of that.
Wood is a fibrous, hygroscopic material. Wood and the products derived from it are plentiful and found in almost every aspect of our lives, from rich wood paneling to newsprint, paper money to the fine furniture you can buy with it. Humidity plays an important part in the value and life of wood products.
We have a interesting property of wood, and we identify it by calling it an equilibrium moisture content. That means that the wood will be in equilibrium with a certain relative humidity and temperature. If the moisture content of the wood varies very much, it can change the strength properties as much as 10 or 5 to 10% for each 1% change in moisture content.
The wood furniture building manufacturing business is a rather complex art with a lot of carefully monitored factors that go into the manufacturing process. One very important area is the control of relative humidity in our factories for a variety of reasons, particularly important in the wintertime. The summertime in our area of the country in Michigan, relative humidity generally is high. In the winter times, of course, it's very dry, and we have to artificially introduce moisture into the air so that the various wooden materials that we use maintain dimensional stability.
Here in Washington, D.C., they keep all those things by which we measure our growth, from our early tools and implements to the latest vehicles we made for the exploration of space, from the documents that provided the foundation of our society to the latest photographs transmitted from outer space that inform us of our celestial neighbors. All of these are here to see, but once again, humidity plays an important part. Proper humidity levels must be maintained if all of this wonder is to be preserved for our children and for our children's children.
When relative humidity is increased, paper will expand. When the relative humidity goes down, the paper will contract. These changes have a profound effect on records which are made up of composite items, in other words, a paper substrate and a layer or image on top of it, which may contract at a different rate from the paper itself. When these occurrences take place in paper records, cracking, distortion of the image, ultimately destruction of the records can occur.
There's no question at all that humidification of the interiors of museum buildings and collections is absolutely vital in the North American climate for the well-being of objects.
As nearly all of these experts have pointed out, it is not just humidity, but the maintenance of proper levels of relative humidity that's important. Too much moisture can be as damaging as too little. So accurate control of humidification is a necessary consideration.
Our most important concern with regard to humidification related to human health and comfort is the creation of an environment suitable for the growth of microorganisms. Bacteria, viruses, and fungi are the most important factors that contribute to health problems among building occupants.
Another effect that relative humidity has on archival collections is that increased levels of relative humidity can lead to growth of mold, encouragement of insect activity, and actually enhance chemical degradation of the cellulose substrate of the paper.
What we sometimes neglect, however, is that humidity that is good for the object can in fact damage the building. And this happens for this reason, which I can demonstrate on this diagram here. Here we have a cross-section of a museum building in the winter. And if we humidify the air inside, we have a situation like this, where we have a high dew point inside. And that means that as the air penetrates the wall, as it inevitably does, it cools, and the relative humidity goes up until it reaches the dew point here. And at this point, you get condensation within the wall, and water forms within the wall. And two things can happen then. You can either get a movement of salts that then recrystallize and break up the wall on the outside, or you can get ice forming within the wall. And if I take away this diagram now, and we look at a cross-section of a real wall, here is the outside, and here is the inside, and you see the line of damage here, where the stone has been broken apart, so that when one is installing humidification equipment in a building, one has to look at the structure of the building and at the local climate and do calculations to ensure that either the building can stand condensation within the structure or you're prepared to slowly lose the building.
We've looked at what humidity is, what we mean when we say it's relative, and how to measure it. We've examined how humidity can be transferred to and from hydroscopic materials, the evaporative cooling effect of this transfer, and the resultant energy savings that can be realized under some conditions. Finally, we've heard from experts and authorities about the importance of humidity to their fields. In doing this program on the East Coast, I've learned something too. I've learned what they mean when they say it's not the heat, it's the humidity. In the second tape of this series, you will learn different methods of humidification and how each responds to different problems and environments. We'll also take a closer look at two devices which use steam to humidify the surrounding air.